Is it okay now?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So yeah, so it's automatically got disconnected. So let's start again. That's what I was trying to say is that now this probability or the opacity function, which we say is the reaction probability, is a step function, right? So that means I had let me draw it again. This is drawing is gone. Yeah, so if it is something like this, we say that the reaction is going to take place if it is coming within the B max, right? So that is my B max, right? So pi B max square is going to be the reaction cross section. Now the probability function what we take, even it comes within this range, the probability is going to decide, right? Now probability what we assume like this, if B is greater than B max, right, then reaction is going to be not taking place and probability is going to be 0. So that means this B is going to be somewhere higher than this B max. There is no reaction because the probability in that case is going to be taking place. Probability of reaction is not going to take place and probability is going to be 0. But if it is B less than B max, whatever the B max value, I am just showing it here this value, but whatever the B max, it depends on the reaction. So if it is less than that, and definitely reaction is going to be taking place and the probability we take is 1. Right. So with this, then what is going to be the effective reaction cross section? So that is if you look at something like this, here what we get is that, let's say this same picture I am drawing it in a different. So this is B actually. Now A is coming and this is basically the line of the where B is sitting. So if it is B is 0, so that means A is here, so there will be head on collision, right? But it's not always that. So we are taking a sample of B is away from this. Now when it is coming with a impact parameter B, so that means it is the radius of the ring is like this B, and if it is coming within the range dB. So if you look at here, so this is the B and this is the width of the ring, right? So now if A is coming within this ring, right, then what is going to be the cross section? Only the strip of this ring, right? So that is basically nothing but the area of the ring is going to be twice pi B dV, and of course I need to multiply with the reaction probability, that is PV, what we discussed in the previous slide. Then only I am going to get the reaction cross section. So that is nothing but basically the called the differential reaction cross section. Differential in a sense is that only because of this tree. Now if I want to get the total cross section, then I should integrate this d sigma r from 0 to B max, whatever the B max value reaction is going to take place, that if we need to integrate, and that is called the total cross section or the integral cross section or whatever you say. So that is sigma r, which is nothing but the integral of d sigma r. Now if we replace this here, right, so that is going to now PB I am taking 1 That is because we have used this step function, right. So as long as it is within the B max, the reaction is going to take place and PB is going to be 1, right. So then taking PB is 1, and if we integrate this from 0 to B max, we are going to get pi B max square, right. So that is kind of the reaction cross section we are thinking like if we are thinking kind of it, that reaction is going to takes place from a distance at maximum B max distance, right. Now if we think classically, so that means it's kind of hard sphere model, then this is going to be pi d square. D is the diameter of the molecule, right. So okay, so this is basically the pi B max square. Now if we think about classically the hard sphere, then it is going to, the value is going to be actually pi d square. D is the diameter, that is going to be pi d square, right. Now so that is the difference between the hard sphere and real collision, is that as the B max can be larger than D, because from larger distance also there can be change in electronic distribution between the colliding partner. So actual reaction cross section can be larger than the simple classical hard sphere model pi d square, right. So this example, I think we can get little bit of idea if we go for some reaction which is taking place called the in a Harpoon mechanism way, right. So that is I start with the question here is that what is basically if we look at a reaction experiment, then what we get is that like for alkali atoms, when it collides with halogen molecules, right, then the reaction cross section is going to be quite large. So that is 100 angstrom square. I mean, you can think about this is larger compared to your normal reaction what you can think of, right. Now how do we really explain this? This was done by Michael Polanyi long back, and it was kind of like a flame experiment. He tried to do it, and he observed that these cross sections are going to be normal larger, much larger than normal reaction cross section. Then he tried to explain this using the Harpoon mechanism, right. So let's take one example, then we can do it in a better way. So consider the collision between the potassium and bromine molecule, right. Now what do we expect? Normally we should get like KBr plus bromine is going to remove, right. So I am going to have this is K plus Br, and then finally I am going to get KBr plus Br. But in between, what happened? What happens is that like it is going to form a temporary ion pair, right. So it's going to form K plus and Br2 minus, and because of this there is a Coulomb interaction, and that Coulomb interaction is going to takes place over the exceeds the normal your interaction, which is interaction between these two, which are basically van der Waals interactions, right. So, because of this ion pair, this is going to be stable for sometimes, but then this KBr is going to be formed and a Br is going to be rejected, right. How really it is possible, right. So, you can think about like this, like let us say I am having Br let us say I am having Br here, Br2, that means bromine gas. Now, potassium is coming from far distance, right. Now, think about a bit, potassium is having outer shell electron, single outer shell electron, right, and ionization potential of this electron is pretty low, right. And on the other hand, Br molecule, if you think about, its electron affinity is quite high, right. So, then what it can happen, this electron of this potassium from large distance can be donated to this bromine. Once it donates this, then we are going to get negative charge, right, and then this is going to be positive charge here. Once this charge separation takes place, now it is the Coulomb interaction which is going to bring them closer, right. And that is why it is the ion pair K plus Br minus is formed, right. Now, after that is going to go to the Kbr and Br, right, because it has enough energy where the Br when this Br bond breaks, right, and this bromine atom is going to be rejected, right. So, this is called kind of Harpoon mechanism. This Harpoon mechanism, in a sense, this electron is used as a harpoon to catch the Br2 molecule and then pull it back with the rope, which is nothing but your Coulomb interaction force, right. So, that is, if I summarize something like this, so the metal atom which uses its valence electron as harpoon, and in order to pull the halogen molecule, employing the Coulombic interaction as a rope, right. So, this is kind of I hope you know what is harpoon. This harpoon is nothing but the way if you ever have done the fishing. So, to catch the fish, we give some food, and that food is pin up with a harpoon. So, harpoon looks like this, like a J, and it is connected with a rope, right. So, this is connected with a rope, and rope is connected with a stand which can be anything like bamboo and all these things. You have a machine here which can roll this thread, right, and this is called the harpoon. We give food here for the fish to catch the fish. So, it is, that is why normally what we do, we throw this harpoon with the food, then when fish eats this food, then we roll it back and it comes closer, right. So, that is basically the harpoon mechanism what we basically proposed for this kind of reactions where the alkali atoms are going to collide with halogen molecules and the reaction cross section is going to be quite large, right. So, this is sometimes like it's like a Hindi movie, like we can think about like hero heroine, like when first made this love at first sight, that is a kind of comparison you can think about, like in a marriage ceremony, like you have heroine is there and then hero is coming in, and from long distance they fall in love, and after that the rest of the story, then they get married, they have a family like that. So that is just a joke, but that is kind of a comparison you can think about what we think about the Harpoon mechanism. Okay. Now, I would like to explain this in terms of the realistic forces, how really it is going to take place. Okay. Now, look at this drawing. Here is the I have taken this potassium and Br2 only. This is like covalent interaction, this potential, right. This is covalent interaction. So, potassium and Br molecule are far apart. So, I am somewhere, let us say here in the asymptotic zone, right, and this part is K plus Br minus. So, that is ionic curve, right. So, that is Coulomb interaction, right. Now, the electron can be transformed from potassium to bromium, potassium to bromine molecule at certain distance, not beyond that, right, and that distance is shown here by Rx. Rx is nothing but the crossing point of this potential. Is a kind of van der Waals potential, which is just interaction between neutral potassium and bromine molecule, and this is the ionic curve when there is a charge separation. Now, this Rx, which is nothing but the crossing between this covalent curve and the ionic curve. So, what does that mean is that, like when the system comes here at this crossing point, the electron can be transferred from potassium to bromine, and then it follows this Coulomb interaction path, right. Before that, it was coming like this on a covalent interaction, through covalent interaction, right. Now, here I have shown this delta E 0. Actually, this curve is going to asymptotically merge with this like that. Now, this delta E is what? This is nothing but, like if you look at here both potassium and bromine 2 are neutral. Now, here potassium is K plus and bromine 2 is minus. So, that means one electron has gone from potassium to bromine. So, that means this is nothing but is something like difference between the ionization potential of the metal. So, metal is my potassium, so this metal is my potassium. So, that is ionization potential of metal minus electron affinity of the halogen molecule. Okay. Again, the annotation is not working, but yeah. So, that is the delta E. So, delta E is nothing but the endothermicity, right. So, or endoergicity, whatever you say. So, this is difference between the ionization potential of the metal. So, that means the energy required to remove one electron from the potassium minus the electron affinity of the halogen molecule Br2. So, that means energy release after accepting this electron by a bromine molecule. So, this difference is delta E 0, right. Now, this energy is basically endothermicity. Now, this energy, if it is sufficient to get the electron transfer where it should be equal to the energy between the Coulomb interaction, right. So, this much energy basically, let us say this is endothermicity. So, that means this much energy I require to go for the ionic curve. Now, where come that energy is going to come? Now, that energy is going to be coming from the Coulomb interaction when it is coming following this curve, right. So, therefore, this at crossing points you can think about the two potential are going to be same. One is the covalent potential and the sum of this ionic plus endothermicity. Let me write this or bring the this is the ionic potential, which the resultant potential is because of this is like E square by 4 pi epsilon r. So, r is the distance and E is nothing but the charge of this plus and a minus. So, that is why E square plus delta E energy required to form the ions, right. Now, what is the covalent part? The covalent part is going to be simply the covalent potential, which is kind of van der Waals interaction. Let us say that is going to go some constant C6 I have written, because this is sixth order is going to be 6 r to the power 6. So, this is van der Waals interaction, van der Waals force, which is covalent like this. Now, when these two terms are going to be same, so that is at the crossing point, at that time only the electron transfer is going to take place, right. So, that is the relation we are going to use this to find out what is going to be the reaction cross section. So, that means at Rx maximum distance, at Rx the electron is going to transfer, beyond that there is no electron transfer, right. Okay. Now, in this case, if you look at this curve and also if you realize the van der Waals force, which is on the right hand side, is going to be almost negligible, right. So, this van der Waals force is going to be almost negligible and it is going to be taken to be 0, because if you look at here this potential, there is a small dip here, but other than that it is like when it is coming like this. So, that is going to be 0, right. So, therefore, we can put right hand side is 0, again the annotation is creating the problem, right. So, this right hand side is going to be 0, and then we can get what is going to be the approximate Rx value, and we should be able to calculate the reaction cross section, right. Okay. So, using that relation, now you can find it out that if we take this constant is this, and then Rx, that the crossing distance at which electron is going to transfer, is going to be approximately E square by delta E 0, right. And if we replace all the constants, then what we get, this value is going to be approximate, this value is going to be 14.4 is constant value divided by this endothermicity is delta is 0. If we express in electron volt, we get Rx in angstrom, right. So, that is the way you can calculate the Rx value, right. Once we have Rx value, we can calculate this reaction cross section. So, that is going to be pi Rx square, which we is going to be the Bmax square. So, that is something like this. So, my annotation is not working, so that I could not write it. So, if you look at here, then it is going to be pi Rx square. Now, look at this, the value of Rx is going to be just little less than 6, right. So, if I make it square, that is going to be somewhere like less than 36, of course, and then pi is going to 3.14. if you multiply that, so that is going to be 100, near about 100, right. So, therefore, we can explain this Harpoon mechanism using this you explain this larger cross section using this Harpoon mechanism, right. Okay. So, I am going to stop here, and if we have any question, then we are going to discuss.